those of you guys just joining us, the kids wrote down at least some of the notes that are up on the board, and then they were working on test correction questions that they had from each other. But right now, a couple of quick logistics. We have a test next Tuesday. We're in our final section, section 2.7. It's a hefty one, which is why homework is not due until Thursday. But we're going to get through enough examples today that I think you can really tackle it tonight. You can come into zero period tomorrow morning. BC kids should be more than capable of helping you guys with these related rates. Maybe not for all of them, but for quite a few of them, they're like me, and it's like their favorite type of word problem. Doesn't mean it doesn't get tricky, but if you get into the rhythm of seeing this problem, knowing what to do, which right now this entire homework is just related rates. It's not like a homework that's all these different types of word problems. You have to figure out what to do. They're all related rates. We'll rehash just a little bit. I know there were a couple of you guys absent yesterday as to what's going on, but we'll talk about this page that kind of summarizes what to do. It's not a forever card, because I don't necessarily need you to have word for word memorized these 4 things. This is just for this section. There are 2 yellow boxes, one that we saw yesterday, one that we're seeing today. The main idea, the main point, the summary of what you need to remember is in those yellow boxes, just not word for word memorization. Let's see. This is also the last week of October. Speaking of tomorrow being a zero period, have any of you guys noticed that October week 5 was blacked out?
Yeah.
Weird, but I'm supposed to get a stamp this week. Well, usually that box would have been open, and then the first week of November would have been a catch-up makeup week as well as another stamp necessary. So I usually give a week of grace. This week is your week of grace. So tomorrow could be a makeup box. Does that make sense? Now, some of you might still come just because you're like, I don't come necessarily for the stamps. I mean, I do, but I also come for the donuts and the coffee and the collaboration, whatever. That's fine. Like, everyone is still welcome. There is nothing like, oh, it's a black box, I shouldn't come. Well, no. I mean, you definitely, related rates is hard. And you have a test coming on chapter 2. Some of you guys have gotten behind for different reasons. So anyway, just wanted to let you know this is the makeup week. So that stamp sheet is due, turned in on Monday. And then you're going to get one more stamp sheet for the semester for November and December. But it's short. There's not as many, because we don't have as many weeks. But anyway, this is the makeup week stamp. So you guys can be coming in. Remember, if you're missing multiple boxes, lunchtime, period 7, after school, tomorrow morning. So you have multiple days to catch up if you've fallen behind. Yeah? Tutoring. Thank you. Tutoring is due when? Yeah, all my AP, weighted, honors, etc. classes need to have 4 hours of tutoring each semester. Our 4 hours are due basically at the very end of finals week, not necessarily our final, because it isn't at the beginning of finals week, but the end of finals week, because kids study for finals, and if you can help them, that's great. But along those lines, I just want to let you guys know where my Algebra 1 class is right now. They are starting today factoring.
Nice.
Now, they factored out a GCF yesterday and last Thursday, and last Wednesday-ish. Anyway, but they're starting factoring. And if you guys remember Algebra 1, what's one of the most complicated topics in Algebra 1? I have to review it in pre-cal and in calculus. Yeah, factoring. If they could learn it well now, think about how much easier their life would be. Some of you did learn it well in Algebra 1, so you were ready for Algebra 2 and for pre-cal and for calculus when we have to factor. And some of you are like, oh no, I still struggle with it. If you could help them with a whiteboard with factoring, you would make a lasting impact on their mathematical careers. Like, it's huge. And some of you are like, I can try factoring. Awesome. Now, quick warning, if you do tutor my Algebra 1 kids, like, come ask me. If you're like, give me an Algebra 1 kid, I would love to work with them. I'll figure out, and you can work with them and probably bust out your 4 hours over the next couple weeks, meeting with them once or twice. But if you do work with them, do you know how I've shown you, like, multiple methods to factoring?
The X method.
If you tutor an Algebra 1 kid, or even an Algebra 2 kid in factoring, or even some pre-cal kids probably still need factoring, they need to find a way that works with them and just stick with it. Does that make sense? Like, if it's the X, use the X, but like the star method. If it's the box, use the box, but maybe some of you don't know the box method. If it's guess and check, if they can get guess and check down really well, and that's the way they factor, they'll be fine. They just need to get a method down. So maybe play with different methods. but then you just have to figure out which one works better for you and have them choose it and stick with it. Otherwise, you're going to confuse them. And some of you know that. You're like, well, there's an X, there's a box, there's a grouping. You have to find a way and stick with it. Does that make sense?
Uh-huh.
Anyway, just want to let you guys know that because I was about to write up on the board factoring, and I'm like, oh, this is a perfect time for older kids to tutor younger kids and be like, I've been there, but it shows up like multiple years, and it's something you really want to get now because otherwise, man, your life could be awful if you just never learn it. Anyway, thanks, guys. That's my spiel. Let's go back to related rates. Sound good?
Yeah.
Okay. Test, put away. Now's not the time. Test, put away. Now's not the time. Here we go. Related rates. Yesterday, what was the illustration I had up on the board for us to look at, illustrating the fact that in one situation, one simple thing, well, okay, I'm just going to tell you what it was. One simple thing, like what was happening to this conical tank. What was going on? The one that was showing and it was moving. It was filling up with water, right? And as it was filling up with water, question, what were 3 different quantities that were all changing? Volume was changing because more and more water was being was contained in the container, right? It was flowing into the water hose or something. Volume. What else?
Height.
The height of the water in the tank, that was changing. And then what else was changing? The radius, because as it filled, wait, what happened as you guys watched it yesterday on the screen? It got slower because it had to cover more surface area as it filled up. So each unit of height to go up, as the height increased, the surface area increased. And since the surface area increased, it took more area, or it needed to cover more area, therefore it would rise slower. Constant volume, because my water hose was just pouring in at a constant volume of, I think it was 2 if we brought it up again. Constant volume going in. Water hose is just spewing out water. But the height was going real fast for a bit and then started slowing down, and then the radius was increasing at a different rate as well. And so then we talked about, okay, a cone has this geometry formula behind it, yeah? That relates those 3 quantities, volume and radius and height. There is a volume geometry formula, but that's static. We talked about this more in period 6. It's static. Like, give me a radius, give me a height, I'll give you the volume. Give me a volume, give me a radius, I'll give you the height. It's one snapshot in time. If this was entirely full or half full, it's like, sweet, give me these quantities, I'll tell you what's going on here. But this shows absolutely no movement, absolutely no change. This is just give me and I'll give you what's going on at one level, at one time. But what we need to think about is, no, it's filling up. Everything's changing. Everything's moving. So we have to bring in this idea of rate. And what finds rates? Derivatives. But why was this not ddx? Time is the guy who keeps on ticking. Time is what's passing as the water is going and everything is changing. Time is my independent variable in this situation. Like with motion, time was the independent variable. There is no x. I'm not even doing x and y. And I mean, I guess I could do something, but there's no x. So therefore, we went over here and questioned what skills did we need to use to take the derivatives with respect to time of this volume formula? What rules, what skills, what was necessary?
Chain rule and
product rule, chain rule, and implicit differentiation. But what was different, I had you guys go back to section 2.5, implicit differentiation, and you saw dy dx's would show up, but they were all the same rate, right? They were all the same differential. What's different now? 1 second we're taking the derivative of v, the next second we're taking, well, second d first of r's, the next second, well, first d second of h's. We have all these different rates, plural, rates, right? We have all these different rates, but bring it back in, it all came from a geometry formula. There's a relationship with the rates, so we have this equation with related rates that hopefully we can plug and chug and solve for what we need to. So we went ahead and took a quick time out and said, what are we looking at? Well, we're looking at the derivative or the relationship of the rates of this volume formula, relating volume with radius and height, and there's movement now allowed where there wasn't a second ago. Anytime you see, wait, what's the box for, guys? for the different whoever's there, right? dv dt, dr dt, dh dt, d whoever knows, box dt. Whenever you see this is representative of, well, it's a derivative, so it must be a rate, right? In context, so it's the rate at which the box is changing. And we talked about that's how fast or the rate at which volume is changing, radius is changing, height is changing. And if that rate is positive, we talked about how the quantity, whatever it is, must be increasing. So when the water was going in, right? When the water was going in, question, what rates are going to be positive?
Rates that are increasing.
Everything that's increasing, and what's increasing as the water's going in? Everything, the volume, the radius, and the height, right? Because as the height increases, the radius increases, and the volume is increasing, true? So all of these rates need to be positive numbers. However, when we went to go do a problem, what was the situation here? It was still a cone, so you could still use the exact same geometry formula, which had the exact same rates. We stole it from over here. But now the water is, look at that puddle. You see it, right? It's draining out of the tank. So question, what are the rates going to be now? All of them? What happens as the volume drains? Negative dv dt.
The radius.
The radius shrinks. dr dt is negative, and the height shrinks. So when we were doing this example yesterday, did you guys notice, even though I was talking about all the quantities increasing in the first example, did you see how dh dt was a negative number? Did you see how dr dt was a negative number? And we didn't plug this into our calculator, but what would happen if we did after plugging and chugging? Wait, we were able to plug in for all of that? Yeah. Because they gave us, now wait, did they actually literally state dh over dt is?
No.
No, remember, they're giving us a whole paragraph just explaining the situation. It's our job to take this scenario and to model it with math. Yeah? And so they told us how fast the height is changing. So we just said, oh, easy, dh dt equals. Now some of you were like writing down all of the words, and I was like, but look, you can summarize that whole statement in this little baby equation. And then the next second they talked about radius's rate, haha. And then the next second they said, find the rate at which the volume is. Look, it's just dv dt. And what's this line stand for, Adam? You're the one that keeps on bringing it up. Such that. Such that R is 1 and H is 2. That finished off the rest of the yellow. Wait, why did I cross all that out? That's important, isn't it? What are you going to do? Draw a picture and say, hey, it's a cone, right? But when you take all of that information and when you plug it into, start with the geometry formula. Yes, you have to ask Siri to Google it, look in the cover of your book, or just remember geometry.
Yes.
Start with the geometry formula that says, hey, I can relate V and R and H. Take derivatives, and you have the rates related as well. Once we had that equation, we plugged and shoved, and we got. But without even doing it, do you guys know what sign dv dt will have?
That's fine.
SIGN, positive or negative? Negative, because if you've done it correctly, the volume is shrinking, decreasing. True?
Yeah.
Okay. What was with the feet cubed per minute thing on the side?
This is multiplied 3 times.
It's volume, good. And we knew it was feet from up above. The radius was in feet and the height was in feet, so then we kept it in feet, but volume is feet cubed. But if we had plugged in, this one would have been feet per minute. Yeah, feet per minute. The radius would have been feet. The h would have been feet. It'd be feet times feet times feet, feet cubed. It would have naturally occurred also if you had just put in the units with the numbers. Does that kind of make sense? Okay. So all that brings us to what you guys just wrote down. True? What you just wrote down was, okay, well, what are we supposed to do whenever we see a related rates problem? Well, first of all, related rates problem. What word is probably going to be stated multiple times in the problem itself?
Volume.
Maybe volume, maybe not. Because the quantities could change, the situations could change. Rate. Mm-hmm. Now, wait. What if they're being really tricky? They might not say the word rate. Instead, they might say something like increasing this fast, decreasing this fast. But what are that still talking about? Rate. Or instead of increasing, decreasing, it could say changing at. Changing, still rate. Does that make sense? Okay. So even if the word rate is not used, usually it is. And usually it's used multiple times because the whole point of this problem, unlike motion, because, wait a minute, hold on. We have a forever card, don't we? We totally do. And doesn't that forever card talk about rates? Oh, it's back here somewhere. Anybody have the motion card memorized? Back to that. Guys, why am I going to the motion card? What are the two different rates that are talked about on the motion card? Velocity, right? Isn't velocity rate of change? What are the two different rates of change shown on a velocity card? Average and instantaneous. Do you see the DT too? Right? Wow. But are there rate problems beyond or, oh, Satan, I never changed that. Sitamanians. Anyway, have we talked about rates before? Yes. It's on the verbal description of the derivative card, the definition of the derivative. Way back in the very beginning, we talked about rates. What's different is you have multiple quantities with their unique rates. Okay? So to figure out who are the givens? Oh, that's easy. You guys saw me do that in that example, right? Let's do a different color to make it stand out. Who are the givens? And I want you to state the info with, you guys are tracking, right? Remember, do you want to write every single word to every single paragraph question in this homework? And this helps your brain condense the information into what you actually have to work with. Does that make sense? So state the given, state the problem, literally. State the problem with the givens and the find, right? So we have the given and we have the, I should have written it smaller, and the find. And when you're doing the find, remember that you have almost always some sort of deboxy T. You have such that. Okay? You have such that. They give you some sort of clues. And guys, whenever you see the word such that, or whenever you think you can put in the word such that, what that is it's a snapshot in time. If you think about the scenario, something's blasting off. Something is blowing up like a balloon. Something is like a balloon. Something is filling up or draining out. Something is rotating. There's movement that's happening. When they say such that, like in the last example, what's happening when, what was it, R is 1 and H is 2, something like that? That's just one little picture, one snapshot, and they're asking what's happening now. So you have to think about there's this movement happening the entire time. Ooh, a ladder falling down the wall, that's another one. Write an equation relating the variables. This is sometimes given to you, but more often than not, some sort of prior knowledge. You guys have heard this in other classes, haven't you? Prior knowledge. In teaching, it's a buzzword for things that you're supposed to be coming into this class already knowing, like geometry, like trigonometry, like, I guess algebra, but you won't really have many algebra equations here. Things that fall under prior knowledge could be things like Pythagorean theorem, could be things like SOHCAHTOA, could be things like all your geometry formulas with area and volumes and surface area and who knows what. So some formula from prior knowledge. Every now and then they might give you some random formula being like, hey, guess what? This is the relationship between the quantities. But I need you to realize that this formula is a static formula. At the very beginning of calculus, we talked about how it's dynamic and not static. Dynamic signifies a dynamic personality versus a static personality. We understand these words. Dynamic, it's changing, it's interesting, it's different, there's movement. Static, not like static cling, but static means no movement. No movement. So this is a static equation, and it doesn't include change or movement until we do what? Derive. Yeah, the big picture is until we derive, until we find the derivative. So therefore down here we take this static equation and we take ddt of the entire thing. Does that make sense? We bring in movement. We bring in change. We say, okay, this is the static relationship. Now we need to figure out how the rates are related, and we can't figure out how the rates are related until we take a derivative. So take a derivative of the entire thing. Don't forget your implicit differentiation. And your chain rule. Because after you take the derivative, you should have multiple rates. Each quantity or each quantity that you want should have some sort of derivative, some sort of rate, some sort of d box dt. And then plug in all known variables. Now this whole plug in all known variables, here's a dilemma. You might, let me put ingredients, it's technically review. You might have unknowns. If you properly set up your given and your find, you know exactly what is the guy you're trying to solve for. But the dilemma is, even though you know you have to solve for them, sometimes you take the givens, like the literal information that they gave you, like, oh, plug in, plug in, plug in, but wait, they didn't give me this. So if you ever get to a point where you're like, wait, but they didn't give me, you have to go back. And here's the problem. You might just have to go back to the clues in the problem, or you might have to go back to prior knowledge. Meaning, there's more to be found. There are multiple times, just thinking about all the different examples that you're going to see, there are multiple times where you're going to go to plug in and be like, yay, I should be able to solve, but they didn't give me. The reason they didn't give it is because there must be another way to find it. So first, you're going to go back to what you were thinking at the very beginning as far as your prior knowledge. What was the information they gave you? Was there some further application of that? Or is there some way to plug in the such that's to the static equation to solve for what you need? Maybe they just gave you the pieces, you had to put it together to plug in down here at the bottom. Or maybe there's some other piece of prior knowledge, and if you want to write it down right now, one of the most common ones they like to do, and we can do this with problem solving tips. One of the most common ones they like to do, well actually, what do I have? We already talked about ddt. We're taking the derivative with respect to time. ddt is going to lead to d box dt. When you take the derivatives of different quantities. Multiple rates of change, meaning they're not all going to match. It's not like all these dy dx's you can put all together. They're separate. dv dt, dr dt, dh dt. They're separate. They have to stay separate. Non-changing quantities. Okay, here's one. Here's one. If in your situation a quantity is not changing, in ours, the water draining out, radius, height, volume, all changing. Water filling up, radius, height, volume, all changing. Can you think of a different shaped container where even though the water might be filling up or draining out, there is a measurement, a quantity that doesn't change? Different shaped container where if the water was filling up or pouring out, there's at least one quantity that doesn't change. Cylinder, right? Because the cone, the radius is changing the whole time. But a cylinder, what's true? Radius stays the same. The surface is the same. Another one could be like a rectangular solid, right? Because then it'd be that square, that's the exact same, or rectangle, that's the same of the surface. Circle, no, because circle changes, right? The sphere changes. That doesn't work. But a cylinder, a rectangular solid, a square, like a cube. Okay, what can we do with non-changing quantities? If they don't change, they're constant. What is the derivative of any constant?
Zero.
So their d box dt of whoever it is, in this case dr dt of a cylinder, would be 0. Their rate would be 0. Now, do you see how that can be confusing? Because if we take that equation just a second ago, let's take out the 1/3, and so the 1/3 disappears from everything but pi r squared h. We would have had a dr dt. They're like, they didn't tell us. They didn't tell us how fast the radius is changing. But you have to think about it and say, oh, what was the radius not doing in its own? It wasn't changing. If it's not changing, what's his derivative need to be equal to? There's an example of how it could get tricky. But let me show you another example of how it could get tricky since we're in this problem solving tip. Oops, whoa. Too intense. We're doing okay. Oh, hey, what does rate refer to? If you see that word, remember we said you're going to see it a lot. Rate? Yeah, we could, to change, you could see changing, you could see moving. Ryan, was that you? Increasing, decreasing? Refers to all those different words, or I should say all these different words refer to rate, but remember all of these point to, right, our d box dt. Whoever's rate, whoever's changing, whoever's increasing, whoever's decreasing, that is a d box dt fluid. Okay, sorry. Going back to that whole prior knowledge. They give you stuff. You try to plug in that stuff. You've done so well taking a derivative. You're like, I'm rocking this problem. And you're like, I'm missing this. Okay. Here's one of the geometric properties that they love to bring up and confuse you with. Proportionality. I was trying to think of how I want to summarize it. Proportionality of the dimensions of similar shapes. I don't know why I've never done this before, but you guys are just interested. Here we go. Proportionality of similar shapes. If you get stuck in a related rates problem, I hope that in your notes you're going to come back to this page and be like, okay, did I do step 1, step 2, step 3, step 4? I think so. Okay, I'm stuck. Did I think about anything staying constant? That derivative is 0. Did I think about, ready? Similar shapes. Let me give you a few basic examples. What if I was to give you something like, large right triangle, right? Has a relationship, a squared plus b squared is c squared, all this sort of stuff. They throw in an angle, it could also have like trig, like sine or cosine or tangent. Who knows what prior knowledge formula we're using as far as the derivative? It depends on what they're talking about. If they talk about a theta, then we're doing like a Socratella. If they talk about just the sides, we're doing like a Pythagorean theorem. But right triangle, okay, no big deal. But what if all of a sudden they bring in a smaller right triangle? What's the relationship between the bigger and the smaller? What's it similar mean in geometry? Same what? Technically same angles. And the same angles. Not same sides, right? He's shorter, he's shorter, he's shorter. Not the same sides. They're not congruent. They're similar. All the angles are the same. AAA could never prove congruence in your whole like ASA and SSS, and AAA never proved it because AAA is the same, but they're two totally different triangles. But what is the same? The proportion of their sides. Ready? So I'm going to go ahead and name him. And this is a little bit awkward and a little bit weird, but I'm going to name him A, and I'm going to name him A. So A is the little guy. A is the big guy. You guys see the pattern? Little a over big A. It's going to be the exact same as little b over big B. It's going to be the exact same as little c. I know. Capital letters, lowercase letters. I know. Angle, sides. I know geometry, believe me. But coming back, kind of. It's not my favorite, but like this. Anyway. Yeah. Well, no, actually, I like the proofs. It's all the
Everything else.
Everything else, yeah. There's a lot of relationships in geometry that you kind of have to have memorized or else you're screwed. But anyway, it's just been a long time since I've seen all of geometry. But little a over big A, little b over big B, little c over the big C, the little a side over the big A side, the little b side over the big B side, the little c side over the big C side. This is key. Because if you know this, this, and this, you can find that. If you know this, this, and this, you can find that. So they might just give you some pieces, and you have to use this similar relationship. It's nasty. It's nasty. But other things like Pythagorean theorem, hopefully you guys would know. I know leg. I can find hypotenuse, or like SOHCAHTOA. I know opposite and hypotenuse. I can find angle. Maybe you don't want to. I know angle and opposite. I can find hypotenuse. Hopefully some of those are a bit more natural, but this whole similar idea, most of you just totally forget as a thing. And they love to forget. Okay, anyway. Whew! What did I just spend a lot of time doing?
Tips.
We just need to get into problems. So why is this homework not due until Thursday? Are we going to get like a problem or two done? Yes. Are there a lot more that we probably need to see? Yes. So tomorrow is just a work day. Does that make sense? But not a work day like, oh, I get to do my homework by myself and get stuck a million times. Like we're doing examples together to help you on the homework you're trying to do at home. Does that make sense? Okay. But if you do not have someone, a BC kid or another AB kid, on your, I say speed dial just because it's a concept, on your like, hey, I can reach out, I can FaceTime, I can text. In this homework, you need to have someone. You need to have someone. Those of you that get stuck and stop, that's not acceptable in this homework. You need to have someone like, hey, can I text you if I get stuck? Because sometimes someone's perspective of, hey, did you think about, makes a whole difference as to whether or not you can solve the problem. Sound good? Okay. Those of you guys that are so independent and so quiet, you can't do that. We'll look at this tomorrow. There's some different translation clues as far as when you see what you can say, but let's just get to a problem. Wait, what?
This isn't exciting.
Where are the words? Is anybody else disappointed? There's no paragraph.
Are we supposed to disappoint?
Probably not.
I'm disappointed.
Probably not. Sometimes the easiest ones are actually the hardest. But there's no paragraph. Then why is it a related rates problem? Who sees it?
I see dx or dt. I see dt.
There are two different rates. See it?
Yeah.
Not just one, but two. Wait a minute. So those of us that kind of cheated on that one forever quiz was that whole equation of a tangent line, and we stole calc VCs and parametric equations. There's an x of t and a y of t. Are they kind of like related rates? Don't worry, that's not us. That's that. Okay. So guys, static or dynamic? Do you see any movement?
Static.
No movement, none whatsoever. Why? There's no derivatives, right? So what do we do if there are no derivatives, but we need to start thinking about rates? Yeah. They all work for us. They already modeled it mathematically. There's an equation staring us in the face. There's a differential and what it equals. There's a differential that we need to find, and there's a such that right there. They did it all for us. This is one where I probably just write all the words. So, all we need to do is say that we can do implicit differentiation. Right? Let's take our static and let's make it dynamic. That's what calculus does. Okay. What do we got? I'm pushing just a little bit. So that's what? It's not an X, it's a T. It's not an X, it's a T. Times?
dx or dt.
Did we forget already?
I was just thinking.
Okay. The rest of you guys, are we okay? Are we just doing it? It's too easy. Think about it. We have to have our U. It's not a dx dx, it's a dx dt. I need it written now.
Plus 2 long.
Okay, keep going. You got it, John.
Sorry.
There you go. See it? Okay, keep going. So then the next one is going to be someone new. John got it, Kyle got it. 2. Keep going. Got it. Plus. Ryan Vika got it. Next one. 4. Times. Andrea, Adam, a lot of others could. Are we good? So now what? Could we try to make this kind of condensed because there's like a dx dt there and a dx dt there and dy? Sure, but what are we ultimately doing? Finding every time he is and plugging in, right? Just go for it. Why not? And then we have 3s and we have 1s. I guess that's it. And we'll see. If we're missing something else, we'll figure it out. There's bound to be a way from our prior knowledge or the clues. If we're not missing something else, then we're done. So then we go ahead and plug and chug. And we have 2 times the x is 3. And we have dx dt, which is -5. X must be decreasing. Interesting. Plus 2 times the y is 1, dy dt, I don't know. Equals 2 times, just dx dt, which is -5. Plus 4 times dy dt. Guys, can we solve this? I think so. The name of the game is to get dy dt by itself. This ends up being -30. This ends up being -10. I can, what would I do? I would probably go this direction. That would be -20. I would subtract the 2. That would be 2 dy dt, -20 divided by 2. Anyone beat me to -10? Am I right? Okay, but I'm right. -30 plus -20 divided by 2. Got it. Units. Nah, they didn't tell us what we're doing. All we know is there's like a point on a graph, and this is the graph, and the point's moving, and this is how fast the y, or the vertical, parametric equations, how fast the vertical is changing at this point on this graph. Okay, but there's no paragraph. That was a letdown. Maybe, maybe not.
Yay.
Okay, here we go.
Wow.
Every time, ready, in homework, I want you to give it a name, and I want you to write down given and found. I want you to give it a name.
Give me a name.
That keeps you from having to write out the paragraph. Okay? So what's the name of this one? Maybe. I would say balloon inflation. Because couldn't the balloon also be deflating, right?
What kind of balloon is not spherical?
Oh, come on. You haven't seen the big red twisty one?
Oh, yeah.
A spherical balloon is inflated, so its volume is increasing at... Okay, whoa. What do you see that we can mathematically model? Spherical. Draw a sphere. Fine. Got it. Wait, when you draw a sphere, why did they only label R? Oh well, keep going. So its volume is increasing at a rate of. How do I mathematically model that statement, guys? Yeah, spherical balloon. I have my picture. Volume is increasing at the rate of. Perfect. Write it down. dV dt. They say increasing, so am I making this a positive or -3? Positive. If they said decreasing, I'd need to make it a negative, right?
Yeah.
Keep going. How fast? Uh-oh, I've just gone into the find category, right? How fast is the diameter increasing when the radius is 1? Can't we say that's how or what dV dt equals when r is equal to 1? Now, why am I about to draw a box? What do we need to think about?
What is the formula?
What's the formula that relates volume with diameter?
Circle.
The formula I know is the volume of a sphere. And the volume of a sphere is V equals 4/3. I know, you would look it up. Pi r cubed.
Where's the D?
No, we have the V. What are you missing?
I am.
D. Wait, hold on. Radius and diameter, that's a thing, right?
Yes.
Isn't 2r equal to D?
Yeah.
You have options at this point because we need, this is static, this is static. What do we need to do? Derive it, make it dynamic, get some change in there, right? ddt. You can either take a derivative as is with what you know, and then take a derivative of this guy and put all the pieces together. You can either take derivatives first, then put together, because we need this d guy in. Or we could just right now say, why don't we just get rid of r and get in d? Does that make sense?
Yeah.
What would you rather? Take derivatives first and then figure it out, or plug in now, then derive? Okay. So then we're not going to stay with this formula. We're going to say, okay, wait a minute, hold on. We do need a volume formula, but we don't want the R one. We want something with D's. So So we know V is equal to 4/3 pi what cubed? Can't I divide both sides by 2 and say R is equal to D over 2, right? And then can't I make that a little bit prettier by 2 cubed is 8, 8 and 3 is 24, well hold on, 4 and 8 is 1 and 2. 1, 6 pi D cubed. Now that's not the traditional formula, but isn't that what I need?
Yeah.
Because now you guys, by figuring this out ahead of time, looking at what they gave us and thinking about it, can't I now get my derivative in? And what's going to happen? dv dt is going to equal, bring down the 3, 1 over 2. There's no product rule. There's only one variable. Check it. What do you think you're going to be able to do?
Plug in DV.
Plug and chug. No, I don't have D. Oh, that's okay. I have a relationship. If R is 1, isn't D 2? See how you have to kind of use all of these different prior knowledge pieces to get to the end? But now all I have to do is plug and chug. Bye, guys. I'll see you later. Go start playing with homework. Go until you get stuck. Come tomorrow being like, I really hope she does an example like the ladder because I'm stuck. Bye.
You plug in DV.
Yeah.